Hello, and welcome to Pre-Calculus, Section 6.3. This section will be about solving exponential equations. So the first exercise I want to run through is the steps you would go through to find the inverse of the function f of x is equal to b to the x. So from what we know about how to find inverse functions, the first thing that we do is instead of calling the function f of x, we're going to call it y is equal to b to the x. So that's step one. So make sure you're taking notes on this. So you're going to write in your notes, find the inverse of f of x is equal to b to the x, and all of these steps we're going through here. So right now, I'm replacing f of x with y. So y is equal to b to the x. The next thing I'm going to do is switch x and y. And then next thing I'm going to do is I'm going to solve for y. All right, so let me write those instructions beside the step. All right, and then the next thing we said we were going to do was solve for y. So in order to solve for y, if my y is up there in the power position, I have to have a way of getting rid of this b in this position or extracting this y out of this position, however you want to look at it. So what I'm going to do is I'm going to take log to the base b of both sides to accomplish that. So I'm going to say log to the base b of x is equal to log to the base b of b to the y power. So next, we're going to say we can cross out this part here and be left with y. So we'll have log to the base b of x is equal to y. So I'm going to write it this way. Y is equal to log to the base b of x. And instead of saying y, remember when we found the inverse of f of x, we call it f inverse of x. And that will equal log to the base b of x. So now we've established that f inverse of x is equal to log to the base b of x, where f of x started out as b to the x. Now we're going to go in the other direction. So this time it says, find the inverse of f of x is equal to log to the base b of x. So my first step is going to be write it as y instead of f of x is equal to log to the base b of x. The next step in finding an inverse is to switch x and y. So we're going to switch places. And the next thing we're going to do is solve for y. So in order to solve for y, I'm going to raise both sides by the base b. So b to the x and b to the log base b of y. So what that allows me to do then is to cross out b and log b there, so I'm left with y. So I'm going to say b to the x is equal to y, or if I say this way, y is equal to b to the x. And then the last thing we do is we replace y with f inverse of x. So f inverse of x then is equal to b to the x. So if I started out with f of x saying log to the base b of x, and I want to find the inverse, I end up with f inverse of x is equal to b raised to the x power. So we're going to employ our knowledge of how to undo exponentials or undo logs in order to solve exponential equations in this section. So we're going to solve this equation, 5 to the x is equal to 11. And I'm going to use the method that I call taking the log of both sides. So what I'm going to say here, when you take the log of both sides, you technically can use any base, but what I recommend is using a base 10 log, which doesn't have the little 10 showing, or using the natural log, which is the same thing as log to the base e. And that's because your answer will come out in a more versatile manner such that you can enter it into any standard calculator. So let's go ahead and do it by taking the log of both sides to the base 10. So I'm going to say log of 5 to the x is equal to log of 11. Next, I'm going to use the power rule for logs, which says I can take this x and put it in front of the log to the base 5, and it'll be an equivalent statement. So x log of 5 is equal to log of 11. Then I can divide by log 5, which is just a real number, on both sides, and I'll have x is equal to log of 11 over log of 5. This is what we call an exact solution and not a decimal approximation. So this is the way I would prefer that you left it. Your homework problems will accept it in this manner, but you could also plug it into a calculator if there was a reason to have a decimal approximation. For instance, if you were trying to graph it or something like that. And let me just show you how you would do that. So this is just your standard Google calculator that comes up. So here I typed in log of 11 divided by log of 5, and I'm getting 1.4899 as my decimal approximation. And your homework problems will also allow you to input either a decimal approximation or the exact log form that I highlighted. I prefer the exact log form, unless you need the decimal to do a graph or something like that. This form would be more useful. All right, now we're going to solve 4 to the x plus 10 is equal to 22. So we need to extract the x plus 10 out of the power position, and the method we're going to use is take the log of both sides. So I'm going to use log base 10 of 4 to the x plus 10, and then on the other side take the log base 10 of 22. And then I'm going to use the power rule for logs that says I'm going to take this power, which is all of this, and I'm going to put it out front here. So I'm going to say x plus 10 times the log of 4 is equal to the log of 22. All right, and then I want to divide by log of 4, which is a real number, on both sides. So I could cross it out, and I'll have x plus 10 is equal to log of 22 divided by the log of 4. All right, now I still have a 10 over there, so I'm going to subtract 10 from both sides. So I have x is equal to log 22 divided by log of 4 minus 10. All right, that can also be plugged into a calculator if necessary in order to get a graph or to have some idea of what the magnitude of this number is, and you could get a decimal equivalent. But once again, I prefer the exact solution. Okay, once again, we're going to take the log of both sides. Log base 10 is what I'm using. So I'm going to say log of 3 to the 9x is equal to log of 20. Then I'm going to take my power and put it out front using the power rule for logs. I'm going to divide by log 3, which is a real number. So I'll get 9x is equal to log 20 divided by log 3. And then I need to divide both sides by 9. So I'm dividing by 9. Now remember, when you divide by 9 and you've got a quotient already on the other side, on the right side, you're multiplying by 1 over 9, flip and multiply. So it's the same thing as saying I have a 9 in the bottom, which then you would write log 20 divided by 9 log 3. So essentially, if you're dividing by 9 here, the 9 goes in the denominator beside the log 3. All right, so this is called your exact solution. And if you had to punch this into the calculator for whatever reason, you would want to make sure that you used parentheses properly around this entire denominator. So once again, we're going to solve this problem by taking the log of both sides equals the log of 26. And then I'm going to use the power rule for logs and put the exponent in front of the log 8. Then I'm going to divide by log 8, which is a real number. And I'll have x over 5 is equal to log of 26 divided by log of 8. And then I need to multiply by 5 on both sides so I can cancel the 5. So multiply by 5 on both sides. So I'm going to say x is equal to 5 in the numerator, 5 log 26 divided by log of 8. And that is an exact solution as opposed to a decimal approximation, and that should be fine. We're going to enter it like that. And if for whatever reason you need a decimal approximation, like I keep repeating, for either a graph or some type of word problem where you really need a feel for the magnitude of this number, you would go ahead and use your calculator, your log button, to get a decimal approximation. Otherwise, this is an acceptable form. This is called an exact answer. All right, here's another one. So this one has a few numbers to undo, and we want to make sure we undo them in the correct order. So the first thing that we would want to undo is the plus 3. So we've got to use our PEMDAS rules when we solve, reverse PEMDAS. All right, so I've got 3 times 2 to the 5x is equal to 54. And then I'm going to undo the 3. Now let me remind you, this is worth repeating again. This 3 and this 2 will never be multiplied together because this 2 is raised to the 5x power, and this 3 is simply a multiplier, like a coefficient out front of this term here. Okay, so I want to get rid of this 3 here. I want to leave this alone right here in this step. So I'm going to divide by 3. So I have 2 to the 5x is equal to 18. Okay, I've got it in the form now where I could take the log of both sides. So log of 2 to the 5x is equal to log of 18. Using the power rule for logs, I'm going to put the 5x in front of log of 2. And then I'm going to divide by log of 2, which is a real number. And I'll have 5x is equal to log of 18 divided by log of 2. All right, there's one more thing to do. I have a 5 that I'm going to divide by. So remember, when you divide by 5, it's the same thing as putting it in the denominator. So I can say x is equal to log of 18 divided by 5 log of 2. This is an exact answer. This is a preferred way to write it. It's not a decimal approximation, but like it's worth me repeating, if you needed a decimal approximation, which we don't need, if you need one for graphing or for some kind of a real world problem where you really want to know how big this number is so you can compare it to something else, then it would be necessary to plug it into the calculator. But this is a preferable form here because this is an exact number. Okay, so now we've got an e to the x plus 5 is equal to 23.6. Now what's slightly different about this problem is if I use a natural log and take the natural log of both sides, then I won't have two logs in my answer because the natural log will undo that e. So I'm going to do this one a little differently. Remember, there's multiple ways that you can express your answer with logs depending on which base you decide to work in. So I'm going to work in the natural log for this problem here because I can get rid of the log on this left side here and only have a log on the right side. So natural log of e to the x plus 5 is equal to the natural log of 23.6. Okay, so remember we've learned that that'll cancel all of that out and we'll be left with x plus 5 is equal to the natural log of 23.6. And I do have a button on the calculator for that, so it's okay to leave it in this natural log form. It's still useful. So now I need to subtract 5 from both sides. So I've got the natural log of 23.6 minus 5. So this is an exact answer. And what's different about the way this answer looks than the other ones is that this one, for instance, you end up with 2 logs in your answer. This one, we only had 1 log in our answer because we were able to use this ln to cancel this one out and only have a log on this side left in our answer. Okay, so we're going to solve this problem a little differently as well, because I'm going to recognize here that 4 and 6 are related exponentially. Okay, 4 squared is 16. So I can think of these both numbers here as base 4 numbers. So I wrote that down. I'm saying solve using like bases because 4 and 16 are base 4 exponentials. And if you do it this way, then you end up not having logs in your answers. You'll end up with some sort of regular, so to speak, looking number. So I'm going to take log base 4 of 4 to the 3x plus 5, and I'm going to take log base 4 of 16 to the 2x plus 3, and I'm going to be able to see that this part here is going to cancel each other out because of our inverse properties. So I'll have 3x plus 5 is equal to, using the power property, I'm going to put 2x plus 3 in front. 2x plus 3 times log to the base 4 of 16. All right, now let's look at log to the base 4 of 16 and see whether that is just some number. So what we're asking ourselves, what is log to the base 4 of 16? So what we're saying here is if you take the base 4 and you raise it to some power, you should get 16. So what we're looking for is what that number in the box is. And isn't it 2? 4 squared is 16. So that tells me that log to the base 4 of 16 is just equal to 2. So I can replace that whole thing with a 2. All right, now it's just a linear equation that we can solve. So we can say 3x plus 5 is equal to 4x plus 6. Or let's bring the x's to the left. That would be negative x. Or I'll bring the numbers to the right. So that would be 1. So we can say x is equal to negative 1. So we're not going to have any logs in our answer if we can solve using like bases. So what you're looking for is whether your original equation has like bases such that you can choose the log that you want to use in order to get your logs to cancel out of your answer completely. All right, so here's another problem where we can use like bases, and we're going to do that. So I'm going to say use like bases so that you will not have logs in your answer. So I'm looking at these bases here, 1 over 2 and 2, and they are related exponentially. All right, so I'm going to say 2 is the base I want to choose. All right, so I'm going to say log base 2 of both sides. So log base 2 of 1/2 raised to the x plus 7 power is equal to log base 2 of 2 raised to the 3x minus 8 power. All right, so these are my powers here. Okay, so the first thing I'm going to notice, the thing that stands out right away, is that I can cross this out here. So let's do that first. And then while we're at it, we can put the power over here in front using the power rule of logs. So let's simplify that equation a little. So we've got x plus 7 in front, log to the base 2 of 1/2 is equal to 3x minus 8. All right, now let's look at log to the base 2 of 1/2. Let's go over here with that. Log to the base 2 of 1/2. So we're going to ask ourselves, base 2 to what power is going to give you 1/2? So remember how we did this? We said first, we know that when you have a number in the denominator like that, it's got to be a negative number right here, a negative power. So if I put a -1 there, let's think about that. I'm saying that I take that 2 to the first power and I put it down in the denominator. A negative power tells you to move your 2 to the first power down into the denominator. So log to the base 2 of 1/2 is -1. So this whole thing over here is just -1. So now I've got x plus 7 times -1 is equal to 3x minus 8. So we've taken all the logs out of our answer. So I've got -x minus 7 is equal to 3x minus 8. Let's get the x's to the left. That's minus 4x. Let's get the numbers to the right. So -8 plus 7 is -1. So that means that x is equal to 1/4. So as you can see, there are no logs in our final answer, and we've achieved that by using like bases to solve this problem. All right, so we're going to try this one last time. We're going to use like bases to show that there are no so that there are no logs in your answer. All right, so I'm looking at my base here 10 and my base here 1/100. Now if I use log base 10, then I'll be able to get this 10 out of here on the first step. So we're going to use a log base 10 here. And so we'll just call it log, because we understand when we say log that it is base 10 of 10 to the x plus 15 is equal to log base 10 of 1/100 to the 3x plus 2 power. All right, so since this is understood to be a 10 here, right off the bat we can cross this out. And we have x plus 10 on the x plus 15 on the left. Using the power rule for logs, we're going to take this power, we're going to put it out front. 3x plus 2 log, I'm going to write the 10 in here just so it looks more consistent with how we're reducing logs. Log to the base 10 of 1/100. All right, now we want to look at this and see what we can do with this part of it over here. So we're going to ask ourselves, 10, my base, to what power gives you 1/100? All right, so we can see the relationship between 10 and 100 is it needs to be squared. So I'm going to put the 2 in there. And then it needs to be moved into the denominator, so I'm going to put the minus in there. So log to the base 10 of 1/100 is equal to -2. So I replaced this with -2, and now I've got a linear equation without any logs in it. So we can solve that. We can say x plus 15 is equal to negative 6x minus 4. So if I bring my x's to the left, I'm going to add 6x to both sides. If I bring my other numbers to the right, I'm going to subtract 15 from both sides and then divide by 7. So I should get x is equal to negative 19 sevenths. So I've got my answer without logs in it. All right, so that concludes all of the examples I have for you for section 6.3. What I want to emphasize is that you've written down all of the steps that you would need to go through if I asked you to use like bases so that there are no logs in your answer. So all of these steps would need to be written out in this logical fashion, showing all of this. Make sure you wrote it all down if you were to receive full points on a problem like this. If you were solving an exponential equation that looked more like this, where I didn't ask you to use like bases, then I would ask for you to use this kind of progression here, like this, and leave your answers in exact form. I don't usually ask for a decimal equivalent, so it's not necessary to give it to me. And one last word. If I asked you to find the inverse of the function f of x is equal to b to the x and explain your method, you would have to show me you used your method of replacing f of x with y, switching x and y, and solving for y, and then eventually replacing y with f inverse of x, just like we learned to do when we were studying finding the inverses of general functions. All right, so that wraps it up. If you have any questions about your homework set, please let me know.